In this video, we're going to discuss how to develop student reasoning and proof. And in the elementary classroom, this is something that doesn't occur spontaneously. In fact, you have to really carefully develop it within a supporting environment. So prior to any discussion of plausible reasoning, it's important to describe some of the factors we have to overcome when we're working with young people. We tend as humans to be able to really solve some amazing problems that would put a computer to shame, but then fail to solve the simplest judgments about everyday events in a logical fashion. And so what we see is the same gifts that we have as human beings that enable us to make these wonderful inferential judgments also are blocked in many cases through abuse of language. And these abuses of language are common in our public discourse to win debates. And they look logical on their surface. And although they comprise a series of verbal tricks that can be recognized, you can convince even the most dedicated cynic unless you really look carefully. These techniques, frankly, have been used since antiquity. If you ever look at formal argumentation, you'll see that many of the techniques used by the ancient Greeks and Romans are still in use today to win debates at the expense of truth. In 2012, Bennett, for example, identified over 300 logical fallacies. It's a little scary. Together with methods, thank goodness, to overcome falling prey to their use. Now, one thing we have to remember as teachers is that language development will precede the development of formal reasoning. We have to be able to talk about a problem situation in order to reason about a problem situation. And so it's not surprising that students often fail to recognize the frameworks where plausible reasoning can lead to generalization and later proof. So at the elementary classroom, we need to reconstruct our classrooms into environments that require a more formal treatment of language, reasoning, and even what counts as a meaningful argument. And one such approach is encompassed by the acronym I created called CARE, where C refers to commonplace, A to authority, R to reasoning, and E to experience. And what I hope to show in this video is that when we take these together and apply them in the mathematics classroom, it'll create an environment that supports student critical thinking and reasoning. I should note that just as many of the logical fallacies discussed by Bennett, we derive a lot of these ideas from classical argumentation, and some of them, in fact, will probably be very familiar to you as readers. So let's kind of start off by looking at this in terms of why should I care? Okay, why should I care? Well, when we talk about the first letter in the acronym C, commonplace, what are we talking about? Commonplace has its origins in oral histories. And those of you who might remember the series of unfortunate events books by Lemony Snicket, the Boudier orphans wrote down their experiences in a commonplace book. And this was a set of understandings that it was assumed that everyone in their inner circle would understand. By the same token, a commonplace would contain literary aspects like Little Red Riding Hood, characters, Hercules, settings that appear again and again in myths, in religion, in modern stories. I had a colleague who described it as pop culture. So basically anything you would expect a young person to be aware of, you would be expecting to be part of the commonplace. When I used to teach, I'd make it a point to even watch a half hour of cartoons each day just so I'd be aware of what are some of the elements of the commonplace and the pop culture that the young children were being exposed to. What we find is each of these elements of a commonplace serve to pass on important aspects of the culture that are so integral that it assumes everyone in the society would be aware of them. In classical rhetoric, for example, a commonplace would be a statement or bit of knowledge that's commonly shared by every member in that audience or community. To be effective in the math classroom, the commonplace should be so persuasive and so universal that it shouldn't require instruction. And you would be able to use it in instruction without extensively having to review it. In geometry, for example, we could expect the informal understandings of cube, like Inhelder described them, as representing something that could be acted upon, that could be handled, that could be pointed out. You could expect students to reasonably be able to differentiate, for example, between a cube and a sphere. As we'll find, elements of this often derive from early experiences with concrete objects, such as dice for a cube and baseballs for a sphere. Now, in order to use this in the mathematics classroom, we're going to have to develop a mathematics-oriented commonplace language. And that's why the very first step in the Action on Objects framework involves a memory recall level of understanding in terms of what are the terminologies, what are the words, what are the vocabulary necessary to describe these objects that we're going to be acting upon. This language needs to be supporting, but it also needs to be precise. And we can take this opportunity to expand on the early imprecise notions upon which they rest. Now, we have to realize that students entering our classroom will have logical fallacies, difficulties in social inference. Sometimes they're not willing to acknowledge that they are even capable of making a decision, and so they accept vague warrants from the teacher over careful reasoning. Not a trivial task. One of our first jobs is to expand our terminology into one supporting mathematical reasoning. And so when we use words, we're going to use them in a very formal sense. For example, let's say that a teacher is using sphere in a geometry lesson. Most elementary students will picture a rounded ball-like shape in their mind. And this memory is very noun-like. It can be described. Its properties can be expanded. For example, a student might think about a baseball. If we think of a baseball, this evokes a different set of properties, however, than if we would have thought about a tennis ball, a golf ball, a ping pong ball. If we think of baseball as being the noun, for example, then seamed could be an adjective that could be used to describe it. We see that a baseball has raised seams. A tennis ball is fuzzy, for example. A golf ball is dimpled. A table tennis ball is smooth. They could have different sizes, bounce differently, have different colors. These are all elements of the student commonplace, although they lack the specificity and precision necessary for use in a rigorous fashion. But from a broader perspective, I hope you see that there's a sphere-like, shall we say, a sphere-like property common to each that could be recognized by all students. And as we develop more formal concept of sphere, this idea comes to play the same noun-like role in the mathematics classroom. In other words, sphere can be an object, a noun upon which we can act. A sphere can have a radius, for example. It can have a location within a coordinate system. A sphere can be made larger. A sphere can be made smaller. There's a lot of noun-like portions of sphere that when we act upon in a verb-like fashion, we generate some mathematical understanding. I hope that you're seeing the linguistic connect here between mathematics as something that we can act upon and the actions we perform. When we act upon something, we are using a process or a procedure. When we're describing the object we're acting upon, it's the noun-like or the conceptual piece of mathematics. Those of you with a background in teaching English as a second language will recognize linguistically the importance of having both of these to make a complete meaning. You have a thing, and then you have a thing that we do with that. We have a noun, we act upon that noun. We have a subject, we have a verb in order to make a complete sentence. Well, in like fashion in mathematics, we have to have the object and the actions upon that object both be well understood in order to really generate strong understanding. Now, assuming that we have a good set of commonplace understandings, the A in our acronym is authority. And I have to kind of laugh here. Here we're having Pythagoras exerting his authority, and his student saying, well, yeah, that's right, but right now I'm looking for someone to make sense of the case that a squared plus b squared might not equal c squared. Now, if we were to rely just on Pythagoras' authority, we'd say, according to the Pythagorean theorem, a squared plus b squared will always equal c squared for a right triangle. If we are to rely upon classroom commonplace, though, we might recognize there's a lot of triangles that aren't right. And if it's not a right triangle, a squared plus b squared does not equal c squared. Both of these are correct. We just have to make sure that we recognize the context. Now, I'm the first to recognize that authority is important in any classroom. However, it can be a very tricky element as a teacher when you're trying to develop student reasoning and proof. What happens with authority is it relies heavily upon the role of the teacher, the relative role of the students, and what sources of information are deemed as being authoritative enough to serve as the basis of an argument or discussion within the classroom. We have to be very much aware of the commonplace we're working within. For example, which of the many potential items of background knowledge are suitable for use in discussion? If you think about it, that means you have to be aware of the student's background, their educational history, their culture. You have to have a richly developed set of content knowledge and instructional challenges, instructional trajectories relative to their classroom experience. What I've found is that teachers who can do this can really serve as an authority. I'm not saying expert here, an authority by selecting relevant items or questions. And when you think in our action on objects model, teacher posed problem, this is one of the major places where teachers can exert their authority. As teacher, we select the objects we act upon, we select the questions we ask, we select how to organize these in terms of mathematically powerful structures, and we select how to create a record of that action such that the mathematics that emerges is both true and meaningful for the student. I want to make one other mention on authority at this point, though. That is that if you just argue from authority, it's true because I say so, true because I say so, true because I say so, that will only suggest to the student what's true. It never will really prove it in their mind. In fact, what I've just done, the use of authority to assert a fact, will in fact block student construction of personally meaningful understanding. Now, students today are pretty up in terms of Wiki and in Google, and they recognize that I can Google things and I can get all kinds of information, but sometimes the authority or source is not valid, and so that authority or source might give you an answer that's not correct. If you Google flat Earth, for example, you might go to the Flat Earth Society website, where there's a number of members that still at least purport to believe the Earth is flat. And so what we have to remember is that much of what's accepted within the mathematics community as having been proved always could be wrong. In fact, there was a conference on interactive theorem proving where one of the speakers said that even if a modern proof cites tens of earlier work, each of which cites tens of earlier works, you might come into a proof and accept it as part of the commonplace and never have the opportunity to review each of the thousands of proofs that took place prior to that. So what we find is that in today's world, it's very difficult for an authority to be truly authoritative in the classical sense. What I find as a classroom teacher, and what I would encourage for you, is that rather than saying that I am the authority, we can say, hey, I'm an expert in this area. Being an expert does not mean I understand everything, but I certainly understand how to find a correct answer through the use of reason from the common places that we're coming from. Which brings us up to reason. I think Thomas Paine said it really well when he said that to argue with a person who has renounced the use of reason is like administering medicine to the dead. Reason is crucial to the mathematics classroom because students are used to thinking in terms of either an emotional argument or an argument that feels good based on what they've seen without really thinking it through. When we examine the division by 9 problem that you all will see later, one of the things we'll see is that could never have taken place in a classroom that didn't have a common place where we recognize the children's understanding of objects. Now, in the elementary classroom, when we talk about reason, we are talking about statements that support a given claim. These are statements that pass, to me, at least 2 tests. First, they provide answers to the challenge, how can you tell? And what would happen if, and then you change something. For example, how can you tell that I'm going to make $20 at the end of the horse problem? That was non-trivial. You had to think about that. You had to discuss about it. You had to communicate your findings. You had to record your findings. What if I change the problem now? I bought the horse for 50 and sold it for 70. I bought it back for 90 and sold it for 110. You see, that's a different scenario. But the thinking we had in the original horse problem would help us in solving this problem. The other thing that I find about reason is that it tends to follow through with the use of because. For example, I can tell that I would make $20 because, and then you'll give the reasons. Now, when we think about the horse problem, that gives us a good experience with what it means to reason and to argue in this rhetorical sense. You notice we're not arguing to win the debate, we're arguing to find truth. And so when we talk about arguing in the mathematics classroom, that's what we're talking about. We're talking about this critical thinking, this discussion, this communication that works in a way for us to understand sufficiently so where we can share this understanding and come together to realize that, yeah, there is a correct answer and this is what it is. This also shows why the diversity in our classrooms is to be so cherished. Each student's going to bring a different perspective, is going to bring a different culture, a different commonplace with them that we can tap into. So we have multiple ways of working together to come up with a correct answer. So what about experience? We're talking about the personal experiences that our children have, and that's what we would like to be developing here. I kind of have to laugh at this hypothetical Roman now. Of course I talk to myself. Sometimes I need expert advice. Well, if we think about an expert as being someone who knows how to use reason and to balance authority and commonplace to come up with a personal experience, I will agree. We often think that as a general rule, personal truths which arise from personal experience should be absolute. We should really go for that. And Piaget would even say that. But unfortunately, they are weaker than empirical truths. For example, you know, truth isn't a popularity contest like we talked about with the Flat Earth Society. Last time I checked, there's over 200 members of the Flat Earth Society who claim to believe the Earth is flat. Within the Flat Earth Society, this is the accepted commonplace, but it has very little to offer towards the vast preponderance of reason, science, and proof I've seen that argues we live on a spherical planet. Experience also is easily swayed by emotion, so we have to realize that as teachers. So we want to make sure that our classroom experiences are based on the classroom commonplace, that we include vocabulary, precise vocabulary that's understood by the students, that we include the ability to draw upon objects that we understand. These objects are part of the commonplace, both from the language we use to describe them and the actions we can perform upon them. Once that's done, as a teacher, I can have the ability to select from the action on objects model what objects we use, what teacher questions I will ask. I even have the ability to select what will count as a representation, what that representation should look like, and build sets of understandings where the experience of the child, the final E in our acronym here, the experience of the child is such that it makes sense to the student and they're able to use it effectively. When we've reached that point, then we've gotten to where we really have built a classroom environment where care is helpful. Commonplace, authority, reason, and experience.